Okay, so today is about energy transfer, and general energy analysis. So first, we will have some definitions about energy that will help us to understand the first law of thermodynamics that we're going to present today as well. So these are, let's say, the content of our lecture, that things that we're going to learn. And the first thing that we need to know is the types of energy, or the forms of energy. Of course, I think from the physics previous study, if your physics classes, you know that there are three major types of energy that we, as an engineer, we deal with, especially mechanical, electrical engineers. They deal with these types of energy. So it's internal energy. That's the energy associated with the disorder motion of molecules. So let's say, for example, if you have any object, and it consists of course, many molecules, and if it's like, for example, gas, when you heat the gas, these molecules will start to move randomly. And this movement actually creates what we call internal energy. So the higher temperature given to this gas, or then the more internal energy that we have, whether it's gas or liquid or even solid. So that's what we call internal energy. And also, we have kinetic energy. You know that kinetic energy relates to the velocity of the object or of the material. So the higher velocity, it means the higher energy we have of that object. And then, of course, this follows this equation. You know that this is the equation of kinetic energy, which relates to the velocity. So v squared divided by 2 multiplied by m. So m is in kilogram. We said last week we only used SI units. So it's in kilogram, and then the speed in meter per second. So meter square per second square divided by 2. All right, so that's the kinetic energy. Also, we have the potential energy, which relates to the level, or from the let's say, what's the level from the earth or from the floor the object is. So, and also relates to this equation, where we have mass multiplied by g. Here g is gravity, and z is the level or the height of the object from the surface. Okay, and if you put all these together, put the internal energy plus the kinetic energy plus the potential energy in one equation, then we call this total energy of the system. Yep. So now we know that if you want to find the total energy of a system, we give it a simple capital E. Then you need to add all these types of energy. Right. So unit of energy is, as we said, it's kilojoule. In this actually equation, this one, we didn't actually add other types of energy. We said these are the major energy types of energy that we deal with. But there are other types which will not be considered in our study, such as the magnetic or electric or surface tension energy. All these types of energy would not be considered like it's very minor. It's not major doesn't have effect on the total energy of the system. In this, for example, in the electric type, we will still use this in our calculations. If there is a current flowing in the system, then definitely this will affect. But as let's say, we will say here, electric is less the statics, electricity from statics or statics electricity. This will like have very minor effect on the total energy. Okay. Is it clear so far?
Yes, sir.
Yes, sir.
Okay, good. Thank you. Right. So this is, of course, we know that if we divide the energy by the mass, then it will be per unit mass. That's really easy. So when you divide the equation by m, m represent the mass, kilogram, then we will get kilojoule per kilogram. So that's what we need to know. All right. Okay, so mass flow rate also is part of any energy analysis, especially when we have a flow entering the system and leaving the system. Then we need to know the mass flow rate, because when you have mass flow rate, there will be energy with this flow. So maybe the fluid has energy. For example, we have steam at high pressure and temperature entering the steam turbine, and then at a certain point inlet of the turbine and leaving at the exit with less pressure and lower pressure and lower temperature. Then this flow actually give us an input, or gives the turbine an energy to rotate the shaft, turbine shaft. So this energy actually relates to the amount of mass associated with the inlet fluid and exit fluid. So mass flow rate is an important factor in energy analysis, and mass flow rate or volume flow rate, both of them we can find following these equations. So the volume flow rate, which is cubic meter per second, relates to this equation, and it is the cross-sectional area. AC is cross-sectional area. So let's say if I have a tube or a pipe, so I call this the cross-sectional area of the pipe, which is the circle. So this actually is AC. So if I know the diameter of the pipe, then I can find the AC, and then that multiply it by the average velocity of the flow inside the pipe. We'll come later on and show you that the velocity is not uniform when inside the pipe. When there's a flow entering the pipe, the velocity actually is not uniform here. It starts with minimum next to the wall because of the friction, and then increases up to the middle, and then reduced again to the other side. So the maximum actually velocity, you find it in the middle of the pipe. So then when we want to find the flow rate, we don't take the maximum or the minimum here, or maximum here. Actually, we take the average between them. And that's why in the equation here, we have average velocity. Okay, so average velocity multiplied by AC, which is the cross-sectional area of the tube or the pipe. Okay. Similarly, for the mass flow rate actually relates to the density and the velocity. And again, we need the AC. So on both sides, in both volume flow rate or mass flow rate, we need the cross-sectional area. So cross-sectional area multiplied by the average velocity, this will give us the volume flow rate actually. So volume flow rate multiplied by density give us mass flow rate. Okay, so you just need to follow these equations, and yeah, that's the important factor here, important thing that we need to know when we do analysis for an open system. We need to know the flow rate, either volume flow rate or mass flow rate. And you can see here in energy flow rate, we need to know the mass flow rate. So we multiply the mass flow rate multiplied by the unit energy, kilojoule per kilogram. This will give us the amount of how much, like how many kilowatts required in this or generated by this flow. Okay. Question?
Yes, sir. When
yes.
we do the analysis, you said we have to know what? There's something we have to know when we do the analysis.
Yeah, we need to know the mass flow rate or volume flow rate.
Okay.
Yeah, but this is only when we have flow entering the system and flow leaving the system. Sometimes, like we're gonna come to this next week, we have closed system where there's no flow at all. Only we deal with a certain space, closed space, and this is actually not something we can find easily in real life. Most of our systems, open system, like something entering the system and leaving the system. For example, the car engine, you need fuel entering the engine and exhaust gases leaving the system, right? And also we need, let's say, flow of water, cooling water entering the engine and hot water leaving the engine. So it's everything is related to the mass flow rate or volume flow rate. So most of the real system, practical systems, requires flow rate. Yeah, but there is some systems that we don't have. Let's say we need to deal with it as a closed system, then we need to apply different. We don't need to use mass anymore. Mass flow rate. We only need to know the mass contained inside the system. We'll come to this actually next week. Yeah, but as a time being, yeah, that's what we need to know. Mass flow rate is an important factor in any analysis.
Thanks.
Okay, good. Any question?
No, sir.
Okay. Just want to see how many students now so far. So you 1, 2. Yeah, same students from last week, I believe. No change. Okay. All right. So other thing that we need to define is the mechanical energy. And mechanical energy is the form of energy that can be converted to mechanical work completely. So if we can convert the energy that we have to mechanical work, we call this mechanical energy. Okay. For example, a mechanical energy of a flowing fluid can be expressed by this equation. Okay. So let's say if we have a flow, or we have, for example, water in a dam, we can use the water in the dam because the dam is like, it has a level, high level than the river level. So we can use this potential energy to produce mechanical work from turbines, hydro turbines, and then this mechanical work can be converted to electrical work or electric power. So maybe this video will just give you a quick or idea about what we are talking about here. 1 second here. Let me share with you the Okay. Sound, yeah. Okay.
Water. It is a unique source of energy, renewable and flexible. It can be stored in reservoirs for a long time, until it is sent down to the hydropower plant.
So you can see that this is like, they just animate this like a particle of water is flowing in the pipe of the dam down to the turbines.
The thrust of the falling water spins the turbine. The turbine drives a shaft, which again spins the rotor of the generator.
So you can see here, this is the turbine, this is the turbine, the hydro turbine, and it's connected to the shaft. Okay, the shaft tries to rotate what we call a generator. So the top here, this is the generator. Okay, so when it's rotate the generator, then we can get electrical output.
And electricity is produced. It is transformed up to high voltage and sent onto the grid, and on its way to giving us power we so depend on. But that's only part of the story. Having done its job, the water continues on its perpetual journey, so that over and over again, it can provide us with renewable, pure energy.
Yeah, that's just explain to you the the idea of potential energy actually, and how we can generate mechanical work and then electrical power from potential energy. Sorry. So if you look to this, for example, this figure, this represents what we just seen in the video, a turbine, hydro turbine, and a generator of a certain dam or a reservoir. And it depends on where we put our boundary. When we do analysis, energy analysis, depends on where we put the boundary. So for example, in this figure, the boundary, what we take is this is our boundary. So everything entering this boundary and leaving this boundary, we should consider. So as you can see here, the flow of water crossing this boundary and flow of water leaving this boundary from the other side. So 0.2 and 0.3 are 2 is inlet, 3 is outlet. Yeah. And if you apply this equation, you can see from the from these variables that the velocity 2 and 3 considered similar or almost equal. And the reason why they are equal, because the diameter d are also equal. So D2 equal D3. So diameter of the pipe, inlet pipe and exit pipe are similar, and therefore, because we said before, remember we said m dot is equal to rho V A, correct? Density of water doesn't change. The area is fixed, right? So, and then the mass flow rate must be the same, because everything entering the system should leave the system. You can keep the flow inside the system, right? So for example, if we have 2 kilograms per second entering the system, it must leave 2 kilograms per second, correct? So, but the change will be either in area or velocity. And because area is fixed, and everything here fixed in the equation, so the only variable is velocity. And because of this, because m dot 1, m dot 2 equals m dot 3, then v must be constant, no more variable. Therefore, we can say v1, v2, sorry, equals v3, right? So we can eliminate this part, this term. And also, the distance between z, between these 2 points, there is no like big difference between them as a level, as the height. And because the height is not much between them, difference in z, not too much, then we can also eliminate this. The only thing here that affect is the change in pressure, because the pressure of inlet flow is much higher than the pressure of the flow leaving the system. Therefore, we only consider now this part of the equation. We can say mechanical work, as you can see here in the equation. The mechanical work can be represented by the change in pressure between 2 and 3, divided, of course, by the density, right? So this is one case. We can apply, we can take the same case here, the same dam, but I can take it in a bigger picture. So I can take the dam, I can take the boundary. This is my boundary. I increase the boundary here now. Okay, so this is boundary of the system. Anything entering the system, anything leaving the system, this is my, I should consider. So now, if I take this condition here, the equation here, this one will have different, or we're gonna take different term. So as you can see, the pressure 1 and pressure 2, both of them exposed to atmospheric pressure, the atmosphere, right? Because they are both of them at the same site. I know that there's H between them, but this will not affect too much on the atmospheric pressure, because the height, for example, of the dam is maybe, for example, 30 meters, 50 meters. 50 meters in atmospheric pressure doesn't like make big change, right? So P1 and P4 are the same, almost the same. And also, if you can look to the water here, water at the top of the lake, the water at the top of the river, the velocity is not big difference between them. Maybe the river, the velocity of the water in the river has some flow, correct? But still, again, this velocity, small velocity, doesn't change too much in the energy equation. So we can also eliminate the velocity. So I can eliminate the velocity here and the pressure this time. I only keep the Z, because that's what affect now as a potential energy. So if I know what's the height of the dam, then I can get the energy generated, or the work, the mechanical work of the turbine shaft. Okay, so this is like, again, you can look to this equation here. It's different from this one, but both of them should give you the same answer. Okay, both of them, because we are dealing with the same dam, the same, the same site. No change, but we use different terms, and based on our boundary, system boundary that we took. Okay, any question?
Yes, what's GZ means?
So GZ is the potential energy.
Potential energy, okay.
Okay,
Thanks.
so that's GZ. Yeah. Okay. Right. So just like let's practice this now and see our understanding. This is like very simple application, but if we have wind turbine, you know that there's what now they call wind farm. So do you know an idea about the wind farm? You know what do we mean by wind farm?
Yes.
Yes.
Wind turbine.
Yeah. So why they call it farm? Any idea?
I guess because they harvest energy.
Yeah, correct.
And farm.
They put it like many wind turbine in a certain site. So it looks like, you know, you have trees of turbines. So it's a farm, like a farm of turbines. So they call it wind farm. So this site has a wind farm, this farm is observed to have wind speed 8.5, as you can see. So the wind speed here, 8.5 meter per second. Okay, and from this speed, they generate power from the turbine, wind turbine. So we need to know the wind energy per unit mass, and also we need to know the wind energy for a mass of 10 kilogram of air. And then we need to know per second, energy per second, or kilowatt, watt of this amount of air. If we assume that there's 1,154 kilogram per second entering the turbine. This is the amount of air entering the turbine. So if this is the amount of air entering the turbine, what's the power output that we can have? Okay, so we'll start again from the basic equation that we had. Yeah, so we said that equation of energy. What was the energy, remember? You? Yeah. Next.
KE plus
Yeah.
KE
Or
plus
E squared by 2 plus
potential energy and
EZ. Yeah, potential, correct. Okay, now if we apply this, now for this case that we have, the U, which is the energy contained in the internal energy of the air, the internal energy of the air doesn't change actually, because the air temperature and pressure before and after is the same, correct? Doesn't change because we are at the same site. So this actually will not be considered. It's almost zero. And if you look to the level of the point, let's say I take a point here and a point here. So the inlet point and exit point from the turbine, both of them have the same level of, let's say, of a ground, right? So Z1 and Z2, both of them are equal or almost equal. Yeah. So because of delta Z is almost zero, I can also eliminate this. So the only factor affecting the energy or generation of energy here is the kinetic energy, right? So we need to find out how much energy per unit mass. You just need to apply V squared by 2, okay? So applying this, you'll get 36.1 joule per kilogram. This is per kilogram, yeah? So we just answered the first question per unit mass, correct? Now for a mass of 10 kilograms, we have 10 kilogram, what we need to do, what's the energy of 10 kilogram? This is per 1 kilogram. So for 10 kilogram, we just multiplied by 10, correct?
Yes.
So just quite simple, straightforward. So we'll have 361 joule. And then need per second for a flow of 1,154. So if I sorry?
We divided on 10?
No, it's, look here, kilojoule per second, right? And here,
we divide 36 on 10, is it?
we need at the end, we have joule per second.
Okay.
So what we need to do, this one has joule per kilogram, and here kilogram per second. So if you multiply kilogram per second by joule per kilogram, the kilogram will be removed, will be deleted. We only have joule per second. This is what we want. So then multiplying the energy by the mass flow rate, we will get joule per second or kilowatt or watt, sorry. Yeah? Clear? It's all about the units. Clear?
Yes.
Okay. So that's actually what we have to do. Multiply the mass flow rate, multiply by the kinetic energy per kilogram, you'll get how much watt, and this is in kilowatt. Divide by 1,000, you get kilowatt. So actually this is the output of the turbine. So each turbine in this farm, each turbine has 41 or generates 41.7 kilowatt. Okay. Okay, so that's another example. And if you have a car and you know the mass of the car, this is mass M. We want to accelerate the car from rest to a velocity of 80 kilometers per hour. And as you can see here, the units are not at the same level. So we have kilometer per hour. So we said that the initial units of SI units, the time is in seconds and the distance in meter. So here there's kilometer and there is hour. So we need to convert this when we do our calculations. Okay. So they want to know in 20 seconds, what's the power required of this car? Like what's the engine power that can bring or can accelerate this car from 0 to 80 kilometers per hour? You definitely need the power. So what's the power of the engine? And we said that the power of the engine or any power, if you know the kilojoule per kilogram, okay, or if you know the, for example, kilojoule only, if you know kilojoule, for example, and divided by the time, then you'll get power, kilowatt. So now we know the second, how many seconds we need to accelerate the car. And first, so the time is already given here, 20 seconds, but we still need to know the energy part. So to find the energy, again, we apply the same equation, U plus V squared plus GZ. And this is per kilogram, of course, which you multiply by M, then it will be total energy, okay? So for this case, can someone tell me, please, like, is there change? Well, we always, when you put this equation, of course, when you apply it to a system, we say delta, because in and out, so delta, delta, and delta, okay, which is change between first and last, or in and out, okay? So now, can someone tell me, is there change in delta U? Like as no. Internal energy. The car molecules, or no, correct? So there's no change in internal energy of the car. Then, okay.
There's no change in height either, so I guess
Exactly. So the height of the car, initial and final, the same Z, right? So delta Z equals 0. So same thing, we can remove this. The only change is in car velocity, start from 0 and to 80 kilometer. So that's actually what we need to consider. So this is our term that we need to consider in our calculation. So if you know this kilojoule, then we just divide by time to get kilojoule per second. Yeah, so it's quite straightforward. So you need to put the velocity, delta velocity here, it's 80, but you need to convert kilometer to meter and hour to second. Yeah, so then to solve it, this is what actually need to do. We took only kinetic energy and just substitute the values. 900 is the mass and the velocity initial is 0, final is 80, but 80 now multiplied by 1,000 because kilometer. So it will be 80,000 meter divided by seconds, because we have hour. So the hour, there are 3,600 seconds an hour. So then this is divided by 300,600. Now we converted all the units. The result is in kilojoule, 222. Yeah. Okay.
Yes, sir. A question from the example 1. The
Yeah.
turbine generates 45 point something per second. Is it like
This
how much?
one, the first
No.
first question.
Yeah. That
So
the
can you say
turbine. The turbine generates what does it generate?
this stuff? 41.7 kilowatt.
Okay.
Yeah. So this is like if you want to know the maximum power that you can get from the wind, it's 41.7 kilowatt. Of course, this is an ideal case. This is not the final output because remember, in any system, you have losses. But the maximum that you can reach is 41.7. And of course, there is no ideal system at all in real life. So you always have less than this value. You do not get this value at all. You will get less than this. So probably you multiply it by, for example, multiply it by 0.8 or 0.7 to have the actual output of the system because of the losses. Okay, mechanical losses and friction losses, all these should be considered.
Thanks.
Yeah. Okay. So yeah, so back to this question. So now we know this the amount of energy required to accelerate the car from 0 to 80. Now this is energy. We want to have the power. So we need, just we said, you need to divide this by the time. So kilojoule per second will give you kilowatt. So we know that this energy actually should be within 20 seconds. So if I divide it by 20 seconds, I know how much power I need from the engine. Okay, so actually that's what we did. So the power of the engine must be 11.1 kilowatt. Okay. Question?
Thanks.
All right, no worries. Thank you. Okay, so let's go to the another definition here about the energy, which is the internal energy. The sensible, we have two types of energy relates to the internal energy. We have sensible energy, the portion of the internal energy that associated with the kinetic energies of the molecules within the flow or within the system. So if the molecules of the object has a speed or like vibrates or randomly moves, then we have what we call sensible energy that you sense as a human. You sense it. So let's say, for example, I can, when I have a hot water, I touch that water, I can feel that it's hot because we call it sensible energy because of the temperature, high temperature. So this is sensible energy. Now, this one kind of internal energy. The other one, we call it latent energy. The latent energy, which is the internal energy that or associated with the phase change of the fluid. So for example, if I have liquid and suddenly change to gas, then I must call this is the latent energy required to change the liquid to gas. Okay, or I condense the gas to liquid, then this is what amount of energy I receive due to this condensation. So the amount of heat released in phase change from gas to liquid, or from liquid to gas, or from solid to liquid, and so on. Okay. So this is like, these are two types of we're gonna deal with. And of course, chemical energy that relates to the atomic bond in molecules, and other type, which is the atomic or nuclear energy. The nuclear energy is the amount of energy that associated with the strong bonds within the nucleus of the atom. So we call it nuclear energy. So we're not actually deal with chemical and nuclear here. We're only gonna use these two in our study, this course. Okay. Right, the thermal energy, we frequently refer to the sensible and latent. So latent heat, latent and sensible heat, both of them under the thermal energy. Now, heat is defined as a form of energy that can transfer between two systems. So remember last time we mentioned that in order to have heat transfer, we need to have change, or we need to have difference in temperature between two systems. So for example, here in this figure, we have cold and we have hot, and two systems attached to each other because they are there's contact between these two systems. Then the flow of heat or energy will be transferred from the hot side to the cold side. That's really something obvious. Okay. Now we have, as a heat, we have three definitions. We have heat per unit mass, we call it kilojoule per kilogram, and we have heat rate, which is kilojoule per second. And also we have total heat, which is in kilojoule only. So the total heat entering the system, for example, we know that how much heat we received from outside, and this is, we call it total heat in kilojoule. So we have kilojoule per kilogram as a unit of heat per kilogram, or we have heat rate in kilojoule per second, or we have total heat in kilojoule. Okay, and for example, in this figure here, this is the amount of heat that the system received, 30 kilojoule. Okay, now if I know the mass of the system, 2 kilogram, what's the heat per unit of mass? Heat per unit of mass, you know? What's the heat per unit of mass? Anyone can tell me? Yeah?
So 15 kilojoule.
Yes, correct. Perfect. 30, you say 30 divided by 2. So 2 kilogram and 30 is kilojoule. So that's give us 15 kilojoule per kilogram. Thank you. Yeah, that's that simple. Okay, and then what's the heat transfer rate? Heat transfer rate. We remember we said the heat transfer rate is the amount of heat per unit time. Yeah. So this is the amount of heat we have, Q. We need to divide by the time. What's the time here?
5 seconds, so it would be 6.
Correct. So 30 kilojoule divided by 5 seconds. That will be 6 kilojoule per second. Okay, so that's that simple. So this is like how we do it, how to change from one type to other type, from one heat type to other type. Okay, so, and we defined it already, and it said that the minimum unit that's in joule or use kilojoule, but you need to unify the units, the level of units. Okay. Question? All right. An energy transfer by work. We know that the work is energy. So work is actually energy. They have the same unit. It's in joule or kilojoule. So and it's associated with the force acting through a distance. So an object, let's say with mass m, move the distance, for example, 2 meters, then I can find how much energy in this system or due to this movement. And the power is the work done per unit time, as we mentioned this before. Okay. In thermodynamics and heat transfer, we're going to deal with heat. Most likely we'll deal with heat and work. So the heat transfer and work. This is like our 2 types of energy we're going to deal with. And for any system, for example, okay, we have a sign convention that we're going to use here. So in terms of the heat, any heat added to the system, okay, will take positive sign for it. Any heat released or escaped from the system, then we'll give it negative sign. Okay. Oppositely, if we take the work, any work added to the system, W, we call W for the work, will give it negative sign. And any work generated from the system, W, it will have positive sign. Okay. So that's what we're gonna fix now. So later on, when we use the equations in energy analysis of any system, we're gonna consider these signs. So we know that in entering the system was the sign of this work, and if leaving the system, what the sign of the work should be for that question, for that system. Okay. All right. And of course, we said that if we have a current flowing in a system, then definitely this is going to be considered in the analysis. For example, here, if we have this water tank, okay, a hot water tank, the one that, let's say, use at home for heating the water. So the hot water tank, they use most likely a resistance, electric resistance like this one. So when you have a current flowing in this resistance, when the current flows in this resistance, then start to generate heat, and this heat will be released to the water, and the water temperature will be increased to the temperature that we want. Okay, so then in this case, we can find out how much heat we have or we had from the from this resistance. Sometimes they call it work or they call it heat, doesn't matter, as long as we are using the same unit. So heat rate is kilojoule per second, and this could be like also work rate or power. So the power here in kilojoule per second, it can be calculated or found from Ohm's law. Yep. So you know that power in electric circuit is the voltage multiplied by the current, VI. So in this case, because we have electric circuit, then we can find the power or electric work, electric power from multiplying voltage multiplied by I. So if you know voltage and know the I, then you can easily find the power, and then you use this energy in your calculation. Yeah, clear? Any question? Feel free to ask, please. Don't get shy, because this is your right to ask any question, even if you find it like simple question, doesn't matter, because this is, you are here to learn. So if you have any question, please let me know now.
No, thanks, sir. All good.
Okay. All right. Let me check here. Maybe we have small exercise with Kahoot. Let me stop the recording now. Pause it. Okay, so we're recording now. Yeah. How many students you have? Imad? Where is Imad? Are you there, Imad? Imad, just to let you know, I will use this the participation in this Kahoot. I'll use it as attendance. So I'll take the names here, put it in the attendance sheet. So please enter your name correctly. If I can't see your name, then it means you are not in the class.
Yes, excuse me, sir. This is Imad.
Yes.
Yes, sir. Actually, I'm at a train station. I'll just get to a quiet spot and then I'll join. Is that fine?
Sorry?
Actually, I'm at a train station. Can I find a quiet spot and then
I'll train station?
Yes,
why
sir.
At this time at train station? Why? What do you do there?
Sir, yeah, I just have to go for an interview. So I was taking the class on train.
But you can't do anything in train station. Like, how are we gonna?
Yes, sir. I just came out. It was urgent.
Anyway.
So I'll just join it.
Yeah. Okay. Right. Suzgil, Charles. Okay, Charles in. Luke. Yeah, Luke there. And Nathan. Nathan. Nathan, are you there? So you are not there. Imad, we cannot start. We need to start now. Can you hear me, Imad? Yeah. Okay, so we have 4 students only. I'll take these students as in the attendance sheet. I'll enter them in the attendance sheet.
Can you see my name? Yeah.
Yes, yes, Imad, yeah. Thank you. All right, so now I'm gonna start, and you need to answer the question. So make it like, first you need to make it correct, and then the fastest answer will be considered as highest mark. Okay, so we have 5 questions now. So we're gonna click on start. Okay. Okay, what's the change in kinetic energy here? So for this system, what's the change in kinetic energy? So V1 0, V2 12.1.
Oh.
Choose one of these. Choose it from the site, not from the Zoom.
Ah,
Yeah.
oh, okay.
All right. So you just need to apply the kinetic energy, right? What's the kinetic energy equation?
Well, it was all sort of obvious because it was only one answer in joules, right? Like,
Yeah, correct. Yeah.
I just didn't get I I had the window open, and as I tried to go back, I timed out. So
you were clicking on the Zoom, right? Not on the window, not in the.
no, I knew that wouldn't work. I just I was looking at the question, and then once I realized what, okay, yeah, this is it, and then the time ran out. So
Yeah, no problem. Yeah, just so that's actually, you have two options, either 0 or, because we have a velocity at the exit, then definitely must be a number. But if you want to find it exactly, this is how to do it: v squared divided by 2. This is the kinetic energy. Yeah, correct. Okay, no problem. So 0 for everyone. So next, still everyone at the same level. So let's go to the next. All of you here got 0. So I'll go next. What's the change in potential energy? Now you know what's the GZ. Between 1 and 2. Is Z different? Yeah, correct. Because we said before that both points, they have the same level in and out, correct? So this is Z1, Z2. Meaning that delta Z is going to be 0. Yeah. Okay. I know the time is very limited, small, but this is the challenge here.
yeah, that's why I just clicked the answer with the energy in it, and I went, all right, that'll do.
Yeah. Okay, so Charles first. Okay, third question. What's the change in air pressure? So between 1 and 2, again, look at this and look at this. And is there any change? Delta P? All of them 0, but you need to choose the right units here. Unit of pressure. Yeah, correct. So unit of pressure is Newton per meter square. It can be in kilojoule, it can be in kilojoule per meter square, kilogram. It's not, this is not the pressure unit. So you just need to know it by heart. Okay. So who's all right, so Imad has in the lead now. Good. Okay. Fourth question, shaft work generated from the unit. The shaft work. Or sorry, just W. Kilojoule. per kilogram. So the shaft work, we know that now the only difference is in kinetic energy. So kinetic energy is our work multiplied by, if you want per kilogram, it's per kilogram. So that's actually or multiply by the mass flow rate if you want it in kilojoule per second. So if I multiply this by m dot, this will give us kilowatt, or only this give us kilowatt, kilojoule per kilogram. Yeah. So you have two things, two options, this one or this one. So if this one, you need to multiply by m dot. If it's not the same, then just in kilogram. So that's actually our answer, correct answer, kilogram, joule per kilogram. Yeah. It's a bit tricky. See who's there. Okay, Luke coming. Good, you are close to each other now. This is the number 5. This is the one that will tell us who's in the lead first. What's the input power? So remember, input power is the power of the shaft required to rotate the shaft. So power is only thing here. Hurry up, 10 seconds. Yeah. Yeah. 72.8. This is the input power. So we know that the only type of energy involved in this example is the kinetic energy. And we said kinetic energy is V squared divided by 2 per kilogram. Now, if I multiply it by m dot, this will give us kilo or joule per second, or in watt. Okay, so the answer here is 72.8. Yeah. Okay, good practice. Right, so let's see who's the first. So number 3 is Luke. Number 2 is Imad. Number 1, Charles. Okay. Well done, guys. Thank you for participation. The idea here is to interact and participate and practice some of the principles that we have already mentioned in the lecture. Okay, good. Thank you. Let me pause recording. Right, so we'll continue to talk about different type of energy, how to calculate them. So we know that now how to find the electrical work or electrical power. And also, you know that from physics, work done by a constant force, if you have a force F, and this trying to move a certain object from one point to other point, then we can find how much work can be like work done, in this case, from point 1 to point 2. If we want to move this object from between these 2 points, if we know the distance, then simply just multiply F by S. You can find out the amount of energy, kilojoule or joule. And then if you know the second, then you can find the power divided by the second. Okay, another thing is the shaft work. In many occasions, in many systems, you have shaft work, and that's actually the idea of mechanical power. Most likely it's a shaft work. So you apply a certain type of energy on a system, or try to focus it on the system, and then you move the system, and then when the movement of this will rotate a shaft. So whether it's whether you have wind turbine, or you have hydropower system, or you have steam turbine, all of these must have a shaft to transmit the energy from the system to a generator to produce power, produce electricity. So to find the shaft power or shaft work, you can easily say that if you know the torque T multiplied by the 2 pi n, or n here is the revolution per unit of time, then you can find how much work or how much power if it's in rate. So if it's like per time, then you can find the power because it's per unit of time, per unit of second. But if it's only revolution, then it's the work. So T multiplied by number of revolution of the shaft, then you can find the energy. Okay. And also, if you have a spring, same thing, you can find the work of the spring following this equation. And you can see in this equation we have K factor, which is what we call spring constant. Okay, and that's depends on the type of spring. So you can find it from tables, and you know that for this type of spring, the spring constant is given. And if you know how much deflection between 2 points, then this is actually, you know, how much energy in this deflection, or in how much energy that this spring can give you. Okay. Now we go to the first law of thermodynamics. This is our major principle or major law here in this lecture. So the first law of thermodynamics, and sometimes they call it conservation of energy. The energy, which states this law states that the energy can be neither created nor destroyed during a process. So it should be transferred from one type to other type. So let's say, for example, if I have electric energy, as we mentioned in the, for example, the tank, or electric energy used to rotate a fan. So this amount of electric energy has been converted to mechanical work or mechanical power. So this power will rotate, or rotate the fan or rotate other part of the system. Okay, so that's the first law of thermodynamics. Energy can neither created nor destroyed, but change from one part, one type to other type. So due to this, like energy balance, we have energy balance. Because of this principle, we can apply energy balance for any system. So we say the net change, whether it's increase or decrease in the system, in the total energy of the system during a process is equal to the difference between total energy entering the system and total energy leaving the system. Okay, so to show you this like in an equation, we can have this equation. So energy, total energy entering the system, we call it, let's say, E1 or En, minus the total energy leaving the system, E out. Okay, if the difference between them, if there is difference, this difference must be the change in the total energy of the system. Because if there is energy in, energy out, both of them are not equal, then where did this difference go? Definitely will be contained within the system. So this is what we call change in total energy of the system. And we simply put it in this equation, E in minus E out is equal to delta system. In many cases, this value is equal to 0. We end up with E in minus E out equal to 0, right? So in many cases, system doesn't keep the energy. It's just simply whatever we have inlet, it will leave. But somebody say, like, then what's the point of this? Why we need to put energy in, energy out if there is nothing changed? Well, the answer is the system. For example, if I have, let's say, a turbine, I have a shaft, and I can use this and as an output. So rather than have it in terms of energy as heat, for example, I have this energy in terms of W or power. So it's something leaving the system, correct? So we have now two types. We have heat entering, and the other side, we have work leaving. But at the end of the day, the delta E is E in minus E out will equal to 0 because nothing kept inside the system. Everything is left. Okay. So that's this is the main equation of first law of thermodynamics. And we mentioned before, delta system is consists of these three parts: internal energy, kinetic energy, and potential energy. Right? Okay, now the mechanism here, we said mechanism of energy transfer. If we have this system here, and we have mass in and mass out, and you can see the work and heat. In some system, we have, let's say, work input. In other system, we have work output. Or we have heat input to the system or heat leaving the system. So it doesn't matter if whatever you have, you can put them all in one equation. Okay, so the equation here will also, the total energy equation that we mentioned in the previous slide, will also have heat, will have W, and of course we need to know the mass flow rate. We mentioned before that mass flow rate, if we have fluid flowing inside the system, then this flow has some energy within the flow, within the fluid itself. So we need to consider these three parts, three types of energy in our final equation. Okay, so this is the final form of the energy equation. Then we add to it these three parts. So now we have, as we mentioned before, total energy in, total energy out, and then we add to it Q in, Q out. And also we have work, we have work in, work out. And of course, we said the energy associated with the mass flow here. So mass, E mass in and minus E mass out. The difference, these should equal delta system if there is any change in the delta system. Okay. If there is no change, then we'll give it 0. Right, so at the end, we can put all this in simple equation. We say E dot in minus E dot out, and E dot in is rate of net energy transferred by heat, work, and mass must equal to delta E system, which is the rate of change in internal energy, kinetic energy, potential energy. All right. So you'll see later on in many systems, there will be no change in kinetic energy, no change in potential energy, and no change in internal energy, U. And then we end up with 0. So this part will be, right side will be 0 of this equation. We only have change in these terms. Okay. So this is the general equation of energy defined by first law of thermodynamics. Now, if we want to apply it, for example, for any system now, for example, this system, okay, we can say here, a fan, for example, a fan that consumes 20 watts, mean that if I have power here, of course, the fan requires electricity. So they say that I need 20 watts. I need 20 watts to operate this fan. Okay, so we'd like to see that if this assumption is correct or not. It's really, do we really need 20 watts to operate the fan, or less or more? So the fan should discharge air at a rate of 1 kilogram per second. And the velocity of the air, as you can see here, the velocity of the air is 8 meters per second exiting from the fan. We know we need to determine if this claim is reasonable. We need to find out, is this claim reasonable? Do we need 20 watts, or we need more or less? Okay, so what do you think? What part of the energy equation we can use here? Let me bring you back to previous slide. And you tell me here. If I want to apply this equation, or let me do it this way, better for you. I just do it this way. And probably this one is okay. So if I want to apply this equation, yeah. If I have, do we have, let's say, Q entering the fan as heat? No. So these two parts can be eliminated. Do we have work into the fan?
We have energy. Is that work? Yeah.
Correct. Because this is like electric work, right? Electric power. Do we have work output from the fan?
Yes.
Yes.
Let's say the fan itself, does the fan generate power or consume power?
No, it just consumes.
Consume. So then it means that we don't have work output, because that's only for the system that generate power or work. So because the fan is already consuming power, electricity from the electricity, then we don't need this part. This one will be 0. This one will be 0. Okay, we'll come to this to the last thing. This mass of air, the mass flow rate m dot here of air and m dot of air before and after the fan, are they similar?
No, because you have air leaving the system, even though I sort of feel like you would need a sort of a vacuum and
Yeah,
to
but
have
if,
no air come in.
yeah, but if this is the fan, for example, I have flow, sorry, I keep changing this. Yeah, okay. If I have this fan here, I have flow entering the fan, m dot, and flow leaving the fan. Is it the same amount of air entering and leaving?
Yeah.
Correct. So then, and because the temperature of the air entering and leaving the same, we end up that there is no energy difference between the air leaving and air entering the system. Correct? Because temperature here also, T and T here are the same, almost the same, because the temperature of the air of the room, you just rotate the air in the room, correct? If you have a fan inside the room, what you do actually, you just rotate or circulate the air inside the room, but you don't increase the temperature of the air or decrease it, correct?
Yeah.
So we end up, this also is 0 because there is no change in energy here. So now the last thing here, so now we know that from this side, from the left side of the equation, we have only power n left. From the other side of the equation, we know that delta is also 0. No internal energy of the air doesn't change, correct? We said the temperature is the same, so no change in internal energy. Potential energy, both level of air have the same level from the ground, correct?
Yeah.
Agree? So this is also 0. The only left is kinetic energy, because we know that the air at the exit has 8 meters per second, while the air before the fan almost steady air in the room, correct? So now we end up, we know now our equation is work in equals to KE. Yeah, sorry for this, but I'll remove this everything now. We end up with work in is equal to delta KE, okay, multiplied by m dot. So this is our final form of the equation. You can see now we took the whole equation, but we eliminated the part that we believe that they are not applicable here. We end up with this simple equation. Okay, so going to use this equation to answer our question, our fan question. Yeah.
Yeah.
Okay, so if I go now here, now I know that my equation work in to the fan, which is, they say here it's 20 watt. We need to find out, is it 20 watt or no, not? So 20 means I need to multiply m dot multiply by v squared divided by 2. So it's m dot here is 1, we said kilogram per second. And the velocity, we say the velocity before and after. So before the fan, we said it's velocity of almost 0, because the velocity of the room, air in the room, and it's almost 0. But after V2 here, we have 8 meters per second. So basically it's only 8 squared divided by 2. And we find out the power. So what the power here, can you see it? Can you check?
Should be 32.
So 8 squared divided by 2. Yeah?
Yeah.
So this is 32 watt. It's much bigger than
20. Yeah.
20. So this claim is not correct. 20 watt is not enough to rotate the fan. And of course, we need to consider something else. This is actually the ideal case, 32 watt. But if we add to it the losses, mechanical losses in the system, because we didn't mention this yet, but later on we're gonna mention this. If we add to it mechanical losses, then we will have more. We need more than 32 watt. So basically, 20 watt is far away from what we need, or very lower than what we need. Okay, clear?
Yes.
That's it.
Yes. Any question?
No, all good.
Okay. So now we can go to this solution later on. I can already mention this, so you can take it from the recorded lecture. Okay. Now, in also energy systems, we need to consider something important, an indicator to the system performance, which is what we call efficiency of the system. So efficiency of the system in its broader definition, states that the performance or the efficiency is the desired output divided by the required input. So or we can say efficiency is equal to simply output divided by input. This is the simple form of energy, simple form of efficiency. And for every system, any system, every system has of course different efficiency from the other systems. But give you here a list of efficiency of, let's say, hot water systems. For a hot water system like this one here, it has different, of course, we have different type of hot water systems. Some of them gas, running by using gas as a fuel. So you can find, let's say, this efficiency 55. And you have other type, for example, instantaneous gas system it has more efficiency, 62%. We have electrical electric hot water system, like about 90% efficiency, and the more efficient one is 94%. So you can see that we have different type of systems. Each one has different, of course, efficiency. Yeah. All right. So that's takes us to definition of efficiency. Takes us to other definition, which is the combustion efficiency. Because we know if I, let's say, if I take a boiler like this. Okay, I have a boiler, and it's a combustion chamber. But inside the combustion chamber, I put some kind of tubes and heat the water within that chamber. So in order to have combustion, what we do, we need to have fuel. For example, here 1 kilogram of gasoline, and I need also to make the combustion complete. I need to have air, oxygen. So I provide air to the chamber. So mix the air with the gasoline and then burn it to start the combustion. And from this combustion, I can release heat, and then I have combustion gases. Okay, the output of this combustion, I have combustion gases. So to find out the efficiency here, I need to know the amount of heat released because of this combustion, and divided by the input energy. So here the input energy actually is the heating value of the fuel. So if I know what type of fuel I used, which is here the gasoline, then I can find the heating value of that fuel. And heating value is actually, it's of two types, depends on the content, water content within that, because every fuel contains some water within that fuel. So if the water leaves as a vapor with the gases here, then I know that this is the low heat value. If the water didn't leave as a vapor, only kept inside as a water, condensed as a water, then it will not consume energy. Then this is like the high, we call it high heating value. By the way, in real life, we don't have this because the water will leave as vapor. We can't condense the water inside the chamber because it's like, you know, we don't want water actually inside the chamber because this will cause rust on the tubes because of the oxidation. So most of like the practical cases, we have vapor. So in real life, we use, sorry, I put here, in real life, we use a low heating value. We don't use the high heat value. Okay, but this is just give a definition of the combustion efficiency, how to find it. Okay. All right. And then also we have efficiency of the generator. So overall efficiency of a generator can be defined by this equation. So the overall efficiency actually should consist of all the efficiencies within the system. So if the system has combustion, I should include the combustion efficiency. If the system has thermal efficiency, I should consider thermal efficiency. And also if the system consists of, for example, a generator, I need to know what's the generator efficiency. So if I multiply all these together, I will get the overall efficiency of the system. All right, so each one of these has the definition we can refer to, and we find the efficiency individually of each section, and then we multiply this efficiency together to get the overall efficiency of the system. All right. So let's say like we can apply this on this example here. So we have, let's say, wind turbine that we mentioned before. We use that turbine to generate power from the wind. So if we have the wind here coming from this side, basically this is the input. Okay, this is the input power we have to the system. All right, so if I want to find the efficiency of the system, if I put the boundary of my system like this. So the system here, I make it presented here. It has one input and one exit. So the one input here, Pn, is the wind power, and P output is the electric power. Can you see here? So electric power and wind power. So if I want to find the efficiency of the system, overall efficiency here, I have to put Pn divided by P out. Yeah, this is my efficiency. Okay. Now if I want to take the efficiency of each part, the efficiency of each section, then this is the different case here. I should take it one by one. For example, if I want to find efficiency of this part, the mechanical efficiency, then I know the wind efficiency input to the mechanical box, gearbox or gearbox system. So if I know this input, and I know the shaft power here, then dividing the shaft power by the wind energy, I can get the mechanical efficiency of the system. Okay, so mechanical efficiency is equal to shaft power divided by wind power. Yeah. Yeah, this is my only this part. I'm talking about only this part of the system. So that's how you find the efficiency of each part. You take it individually, you see, check what's the input and what's the exit. Okay, so let me ask you here a question. If I want to take this part here, what's the efficiency here? The generator efficiency. What's the input?
The shaft speed.
Yes, correct. Shaft power. That's the input. What's the output here?
Electric power.
Correct. Thank you. Okay, so that's the generator efficiency. So this and so on, right? So you have now, you know how to find out the efficiency of each section. Now back to the slide. So I can find any part by applying the theory that we mentioned before. Generator, we did it here, P out divided by mechanical. So which P out here is the electrical power, and motor efficiency, we can say mechanical energy output divided by electric power input. Okay. All right, so this is example, and I think we finished about that. Yeah. So this example is actually about a hydropower plant. Okay, and just very simple here. We have this lake. The lake, we have the height of the lake. We have the mass flow rate of the water. This is the amount of water entering the turbine. And also we know how much we generate from this system as electricity, electrical power. The good thing here, we have the generator efficiency given. So generator efficiency is 0.95. That will help us to find out the shaft power. Okay, so if I divide the output here, 1,862 by 0.95, I can find the shaft power. So the shaft power here is equal to 1,862, because this is the output. I need to divide by the efficiency of the generator to find how much input as shaft power. So this is how to find the shaft power. And then if I know the shaft power, I can find the turbine efficiency if I know the input. So the input power, Pn here, basically from previous slides, we know that in a dam, the power of the dam is actually potential energy, correct? Or energy of the dam is the potential energy. If I know the height of the dam, which is 50 meters here, multiplied by the flow rate of the water, I can get the power, joule per second or kilojoule per second. So all these are given now. Then the first step is to find how much energy this dam can give me, right? So if I go first, I find the potential energy here, as we mentioned before. So the potential energy actually, PE is equal to, can someone tell me how much can it be here? Equation. Said GZ. So 9.81 times, what's Z here?
50.
H, 50. Correct. So I multiply by 50 to get, and then multiply this by 5,000, the flow rate, divide by 1,000 to get kilowatt. So this is the amount of input power to the system. This is how much I have as input Pn, which is 2,455 kilowatt. Okay. How much input to the system? So now I know how much input to the turbine. I know the shaft power. Just found, I can find the turbine efficiency. Okay. So we have different things here. So we need to know first the overall efficiency of the turbine generator. So the first question can be easy now found, because if I divide this power 1862 divided by the input power, which is 2,455, I can get the efficiency of the hydropower system, which is 76%. Okay. Now the other question, mechanical efficiency of the turbine. We said that this is the input to the turbine, but we need to know the exit, which is the shaft power. So shaft power, we said simply is divide the generator power by the efficiency of the generator. Okay. So here, when we divide the electrical output by the 0.95, I can find the shaft power. So if I know the shaft power, simply, because this is the output here, P out of the turbine, and this is the P in of the turbine. So divide P out by P in, we'll get 80% mechanical efficiency. Right? That's actually the end of this lecture. If you have any question, please, before we leave, feel free to ask. Hope you have useful time.
Yeah, thank you, sir. No questions.
No questions. Okay. If there is no other questions, we'll see you next week.
Thank you, sir.
Thank
Tomorrow
you.
you have tutorial, so on campus. So you need to go to campus.
All right,
Okay.
see you then.
Thank you.
Okay. Thank you. Good luck.
Good luck. Thanks, sir.
Bye.